But anyways, um, so Dan, we have the CEO of Perseus Materials, Dan Lee here. Dan founded the company in 2022 while working as a postdoc at Stanford, and kind of came under the assumption that if we made alterations in resin material and behavior, that could impact our ability to create composites and maybe be kind of a game changer from that technology standpoint. Dan's company has done work with NSF as well as with ARPA-E, which I believe is the DOE, as a DOE entity. But really an interesting technology that Dan's developed here for large scale kind of composite frames or pieces. So looking forward to that. Dan and his company have just launched and completed some fundraising events, and are looking as we move into 2026 to potentially expand to a facility. So looking for like a 15,000 square foot production facility. So some really exciting things for Dan and company. And with that, I will turn it over to Dan. If anybody has questions, please feel free to raise your hand. If not, we will have time at the end for some questions. So with that, Dan, I'll turn it over to you, and look forward to the presentation.
All right. Hi, everyone. Thanks so much. Yeah, today, and maybe, I mean, well into 2027 or 28, Perseus is definitely a custom polymer matrix composite part fabricator. But I wanted to step back also a little bit and describe the things that motivated us to found Perseus and where we want to be. So the main challenge that we were chasing down. Sorry, I think I'm hearing some echo back from. Oh yeah, sweet. Okay, thank you. The main challenge we were chasing down was the ability to build big and to build fast. These are defining challenges in all sorts of next-gen infrastructure, energy generation, warfare, and to succeed at that challenge and to win at that challenge, we thought that what we needed to do was to achieve scalability, not by building more, but by building different. So today, a lot of the ways that we achieve high throughput, scalability, and size and speed is through robotics and automation, and that's very important. But what also happens, if we look at the costs of that as a function of throughput, they explode, and this is very difficult to afford for most industries. So I'd say traditional aerospace and is one of the very few that can afford it. But if we look at kind of the new sectors that are emerging in maritime and affordable mass, they kind of live on the opposite end of this curve, where you need the high throughputs and you also need them at low cost. So the challenge that we set for ourselves is how do we achieve a cost curve that looks something like this, where we can achieve high throughputs without exploding the cost with equipment. And we're a relatively small team, but we thought that what we needed to do was assemble a core set of expertise that allowed us to approach the problem very differently. So we're a team of 5 engineers, but I want to highlight some of the key perspectives that we bring. So I have a PhD in synthetic chemistry and experience in industrial and process control. I worked in oil and gas for the early part of my career. And then Munir, our CTO, is a materials and process leader and expert in composite materials. He spent 20 years in aviation and brings kind of that rigor and maybe more conventional ways of thinking about composites and the manufacturing, both from kind of the traditional to even through to high throughput. But what we've also done is surround ourselves with advisors in industries that we think bring very important constraints. So I'm going to highlight the middle two here, Ryan and Steve. So these are industry giants from wind turbine blade manufacturing. Now, to us, that is critical because I'm talking about the blades that are 100 meters and they're 300 feet long. And the reason that we think that this is a very important industry to learn from is that wind energy is cost constrained. It has to compete for energy prices like against solar and natural gas or whatever. And so if we look at the total cost of a finished blade that's 300 feet long, it's on the order of $5 a pound. And so that's like an order of magnitude lower than, I would say, high-end aerospace composites. And there's a lot that we think that we can adapt from this industry into things like maritime and an affordable mass. So the insight that we bring on the technology side is that non-natural behavior resins are important to break that cost curve. So I want to break down a little bit more. So if we look at a traditional composite today, They can be made of multiple materials, but in general, you have fibers and a binder or a resin. These fibers dominate the properties, and the resins dominate the processing. And in general, these are notorious to scale in speed or in automation, whatever it is. And when we started, I was an industry outsider. So to me, of course, it was very obvious that these were unscalable. If we look back to the first composites we've ever made as humans, let's say straw and mud, we kind of build them the same way. So like obviously we've upgraded the straw to carbon fiber and the mud to an epoxy, but operationally they're nearly identical. So we mix the stuff together, we shape it, and then we have to wait. And that is really defined by the kinetics and the behavior of that binder. So the way the epoxies cure, the mud dries. It enforces a lot of the very similar constraints. So when we start to think about how do we make step changes in composite manufacturing, we wanted to attack the binder. And we wanted to go not just in like how do we make faster curing resins or stronger resins. We wanted resins that behave on axes that don't even exist today. So if you think about like a traditional epoxy, let's say, or like a snap cure epoxy, they are very different, and they do allow differences in manufacturing, but they exist on that same axis of like how long does it take to cure? Is it on the order of hours or is it seconds to minutes? So to make entirely new processes that are very different and far more efficient, we needed resins that also behave on axes that we don't even think about today. So we, as a polymer chemist, we were digging into literature and doing a lot of research on these very odd behaviors. We landed on a phenomenon that today is known as frontal polymerizations. And that's been known since the 1900s. It's very difficult to kind of induce for all sorts of technical reasons, but I want to show you kind of like what it looks like in general. So this is a vial of our resins that is sitting at maybe 20 Celsius, so ambient kind of temperatures. What we do is that we initiate a curing reaction, and then we can watch it happen in real time. So the top is a completely cured material, 100% cure, and the bottom remains 0% cure. And it happens heterogeneously. So instead of let's say in a traditional cure, you have your whole volume of resin kind of going. If you measure the rate of cure at any point during a traditional cure, it's the same everywhere. In this case, you have like a very fast cure in different regions and 0% rate of cure in different regions. And so this kind of opens up all sorts of new ways to think about how do we do continuous processing of batch-wise processes, and we can talk about all sorts of other things it enables. But what we then did was we took this base behavior that we thought would enable all sorts of different processes, and we built kind of the first core manufacturing technology. So we call this continuous sweep additive forming, and we're mainly focused on developing this branch of it for these structural skins and beams. And this is a picture from our ARPA-E Summit booth. These are the types of shapes I'm talking about. And this is the technology that launched Perseus in 22 and 23, funded by ARPA-E Innovation Cross, which is a kind of entrepreneurship program out of Oak Ridge National Laboratory, National Science Foundation. And conceptually, we also we won the Startup Booster at JEC World, which is the largest composites trade show. And it was in Paris last year. So a little bit more about how it works. Or again, we're currently focusing on beams and panels, and we want to use them for things like spars, stringers, hulls, things like that. So, and I want to show you these a little bit more in detail. These are the digital files that we are converting into the final shape. We can talk about tolerances also in a little bit, but conceptually, we take these. It's like 3D printing in that we have a digital file that we can convert. We use that to control the machine, but we also have a continuous forming process, and I'll show you a video about it. So the way that we think about how this process fits in to all the landscape of very advanced technology. So one of the ways that we can break down here is we have high rates and low rates in terms of like kilograms per hour, and then static tooling on the left and adaptable tooling on the right. And they all have their niches. I'm not saying it's better or worse, but what we're trying to do is to combine a manufacturing process that allows us to achieve kind of the adaptability and low lead times of 3D printing with the low cycle times of processes like pultrusion. And how we might do that. So obviously the way that we're doing that is we're limiting the kinds of geometries and topologies that we're currently able to make, but this is the ultimate goal, a suite of manufacturing processes that can tackle both lead time and cycle times simultaneously. So on a very high, schematic, high schematic level, what we do is so in this one, the machine is kind of reduced to, let's say, that frame. And that in that frame, there are these actuators with a white material, which we use as the kind of adaptable molding surface. So we load our fibers, and like pultrusion, we use continuous fibers. We can pull them through a bath, and then we load them into the machine. But like 3D printing, what we also do is we load a CAD file. And we have a way to communicate with this machine. And as we continue to pull that part through the machine, we can shape it and cure it simultaneously. And if you think about where that frontal polymerization, where that interface between liquid and solid is, we control that very precisely in that machine. And we do it kind of in that plane of the die. So upstream of the die is completely liquid, uncured material. And then downstream of the die is solidified material without a post cure. And so it is a, I wouldn't say it's easy. There are unique challenges with this type of process control, but it's been an interest. So here's a video of our very first, I would say, large-ish piece. So it was about 4 feet wide by 6 feet wide, and the laminate thickness of about 1/2 inch. And if we look here, this laminate started at it's 1/2 inch thick. So here it's flat, and then we use this to demonstrate. And as we're pulling, we're going to change it from a flat to an arc. So here, obviously this is already cured, so it stays flat on the right end, and then it's arced coming out of the machine. And you can see it over here. The reason I paused it here is on the left side, you can see it's very loose fabric. We use 1200 GSM stitched, Ceretex product. And we can use kind of any fiber freeform, but in this case, we use stitched mats that are of unidirectional fibers, and this had 13 layers of glass in it. But you can see over here it's loose. This is kind of, and this is the broad, I would say, engineering heuristics that we kind of think about. This is where we are today. I would say this was last year, and this is where we hope to be by the end of the year. So max chord or width of the currently is limited by the frame of the actuators. We're about 4 feet wide. Our form tolerances are within 0.3 inches. We're working on this, and the laminate thicknesses. So these two these bottom 3 we kind of have to take together. So at laminate thicknesses of 1/2 inch. Now we're talking about molding levels, so we're about 50 to 55 volume fiber fraction. But at this thickness, we can pull at about 12 inches a minute. And that puts us on the order of the production rate of 200 kilograms an hour. And then we're working on all sorts of different ways. So I would say the tolerances are definitely the most interesting challenge. There are lots of trade-offs that we make in this machine. So for example, the harder we compress, so it's mechanically induced, and so we can push harder and harder to compress that composite more and more. And we don't, like, for example, this is one way that we try to think about out of autoclave processing. Like, we can achieve 90 psi, we can achieve 500 psi if we wanted to, because it's mechanically induced. But there are other trade-offs that we make in the form tolerances. So for example, as we squish more and more, the actuators, and as we pull, the actuators bend out of plane. So there are some compromises that we have to make in the current iteration of the machine. It's about 1.5 years old, but we're developing all sorts of new concepts to get to less than 1/50th or 40th of an inch that we're developing now. We're also on the process and kind of energy side. How do we get much higher thicknesses at much higher linear velocities? And these are things that we're kind of developing all. There are lots of moving pieces, is what I'm trying to say. And right now we're in the early stage of doing that. So I would say and we can talk about some of where the properties are today. I would say they're on the order of a standard molded glass composite. Yeah, 50 to 55 volume fraction, with a modulus around 45 gigapascals for elastic tensile modulus. And we're working on all sorts of more advanced testing and what are the trade-offs that we're making, and how do we do non-unidirectional fibers and things like that. And these are things that I assume that these will be where most of the questions, and we can talk about that. But our timeline so far. So in late 2022 was when the company was founded, and in 23 was when the grants awarded for that preliminary CSAF R&D process from the government agencies and developing that. In late 2024, which is where that video I showed you, is where we validated that concept. And also, like, for us, we've really focused on how do we get the throughputs and the sizes before the properties. Not that we're not focused on properties. It's very important, but there are 1.5 million ways to get high quality composites. And what we thought really was missing was the ability to make these large components. And so far we focused on, yes, on the lengths. We can go infinite lengths. The widths, currently we're 4 feet, but it's very easy to just build. It's an 80-20 frame, aluminum extrusion frame, and it's just very easy for us to continue to widen out. And if you think about some of the targets that we're looking at for is wind turbine blades, and so they can be like 12 feet in chord length and 6 inches of laminate, and I mean these are just enormous structures, and so we're developing a lot of these, and then hoping to adapt some of those same learnings and process technologies towards things that look very similar to a wind blade. So we are thinking a lot about shipbuilding, vessel building for USVs and UAVs, and how do we achieve the high rates and for the thick structures that we would need for structures like that. And in 2025, this year, we have spent kind of refining this, improving our properties. We're in the final steps of closing our first paid pilot R&D with a customer for CSAF for a structural component that goes inside an airfoil. And then in 2026 and beyond, we tried to think very flexibly about the types of processes that we're developing. So right now, we're developing the core understanding of controlling this frontal polymerization in laminate production. We're kind of doing a 2-plate design that's like a shape-changing pultrusion, let's say. We have all sorts of, I guess, like concepts for how do we adapt this to things like filament winding, where we can adapt the shape-changing concepts to things like changing thicknesses of the walls and the diameters, introducing soft elbows, things like that for conduit or piping. And the reason that I just bring that up is that we are still very much in the early stages of company development, and if we find a use case where we think we can work to develop a new manufacturing process for that, I would love to talk about that. We're not so bound to this particular. So this current iteration, this machine is for all sorts. I would say we try to think about it. We group by topologies. So it's another one. So any sort of like panel. So whether it's thin or thick, but that topology can all be produced by this machine. The closed topologies of these circles and hoops will be kind of like another machine and process for adaptable filament winding, stuff like that. And then we try to think a little bit broader about assembly strategies, and we'll talk about that too. And then we are also developing all sorts of adhesive-free sandwich structures. So one of the things that obviously in a lot of shells and monocoque structures, it's not just laminate, it's cores, and how do we adapt to that? One of the things that we have found is that we can take core materials and run them through our machine with laminates. So we can basically do a continuous co-cure with laminates over cores. And then we want to take that step even further, not just straight cores or Nomex honeycombs or aluminum honeycombs, but curved ones, or then even taking 3D printed cores that are topology optimized, and how do we expand doing a kind of a almost like continuous lamination, but shape changing continuous lamination, all sorts of things like that. Yeah. So yeah, we're quite young, and we will be a custom component and tooling manufacturer for the next 3 years at the very least. But we're also trying to understand how does this enable different ways to assemble assemblies. So if we, for example, have the ability to, what about you or about a customer can order a large custom structural component, let's say a spar that runs the whole length of this wing, or the shells of this wing, how does that change the way that we design and assemble this thing for more efficiency? And then one of the things that we're also evaluating, again, this is many years out, but is how do we can we really, if we really believe that we can make assemblies a lot cheaper, then we can explore vertically integrating completely to things like shipbuilding, hull design, and manufacturing. These are things that we muse about, but obviously we're kind of like, how do we demonstrate value? How do we demonstrate reliability and quality in the factory environment, and then for customers to then integrate into things that they're using today. Oh, sorry, this is a little bit out of order, but so there are a couple things that I would like to ask of the NCDMM network. One is that we're hiring. We just closed our first fundraise from a fund called Roadrunner Venture Studios, and they're a subsidiary of America's Frontier Fund, and they're focused on domestic manufacturing and American defensibility. And so we're raising money, and we're growing, and as Adam mentioned, we're looking to open a kind of pilot facility in the 15 to 20,000 square foot range over the next year or so. But over in our current R&D facility, which is about 4,000 square feet, we're still hiring a business operations manager, controls engineer, and a polymer matrix composite test engineer that we will hope will grow with us and stay around as the company grows as well. And on the facility side, we are exploring all sorts of it's a very interesting time. I think there are all sorts of state incentives, factory layouts for forward developing. As we develop the first and executing on our pilots, we are learning a lot about our techno-economics. How do we lay out the factory? Of course, there's a lot of knowledge already on machining facilities and composite fabrication facilities, but what can we can start there, and how do we adapt that to what makes sense for our processes and our customers. And then the other thing is that we're also looking for new pilot partners that either own platforms or larger assemblies, or even just do some custom component manufacturing. We're thinking a lot about maybe the structural elements like the ribs, keel spars, and things in boats, as well as the stringer spars and skins on the wings, and the molds as well. So you said you don't want to switch over a structural component. Totally understood right now, but are there ways that we can help on the tooling side? I'm definitely open to talking more about more complex shapes and different manufacturing processes that we can develop together. But I'd say in the 6 to 12 months, we're really focused on this kind of the simpler topologies where the values and the size and the lead times. So this is my email. You can feel free to send me anything. Yeah.
Awesome, Dan. Thank you for that presentation. Really interesting technology, and really good to hear how you guys have kind of grown over the last 2 or 3 years. So I see we already have one question, but feel free now, folks. If anybody has questions, please raise your hand, and we'll go by the order that I see you on the screen. But it looks like right now Alex Steve has a question, so we'll go over to Alex.
Thank you, Adam. Thank you, Dan. Very interesting. You mentioned that you guys are looking actively for a facility. Are you geographically diverse? Diverse, meaning like the nation's your playground? Because if so, I have a deal for you in Ohio. No, like all joking aside, we just got an innovation hub on contract, right? That's state funded, and our mission is to attract businesses to Northeast Ohio to set up shop.
Yeah.
Because we have an existing network, right? So I'll send you. I didn't catch your email now, but I'll follow up with Adam, right? I'll send you an email, set up a separate conversation for us to chat, because with incentive programs, all those type of things part of the play. So hopefully we can figure something out.
Yes, but yes, geographically open, and Ohio does seem like a place where they are really trying hard to attract companies, and definitely, yeah.
Yeah. Cool.
Dan at Perseus Materials. That's my email.
Thanks, Alex. I'll just send you a note with Dan's email, and then we can go from there.
Oh yeah, you just do the intro. Makes sense. Thank you.
Yep. Hi, Gino. It looks like Gino's got a question. Go ahead, Gino.
Yeah. Good afternoon. So I have a question for you. You mentioned you had produced UAV parts or components at the earlier portion of your briefing. Can you expand upon that a little bit?
No, we want to. So we are focused currently on wind blade components, which are larger, and so there is definitely maybe on this, which may be simpler in shape, and so our P pilot is for a component that goes into To the blade, there are analogous components in the wing, and but yes, we're working on that. So one of the other things that we're also exploring now is in the R&D phase, we've done exclusively glass, and then now we're entering the stage of carbon fiber.
Okay.
Yeah.
All right. How far, when you say you want to do this, how far have you gone into investigating it and broaching topics with other people, whether they're OEMs or other folks that are exploring prototypes?
So I'd say it depends. I think if you want a spar or a stringer, for example, give me 8 months, 6 to 8 months. If you want a structural skin that's a sandwich, yeah, maybe 16 months. Yeah, but I think this is one thing that I'm also learning. Investment is a wild game changer. I would say the pace at which we are moving is changing so quickly. But I would be happy to keep you abreast of where things are with us.
Sure.
Yeah. Photos.
Thank you.
Yeah.
All right. Good question, Gino. Ben DeMarco, I see your hand up. Go ahead, sir.
Yeah, I joined a little late. You may have covered it, but I'm just curious, Dan, some of the composites folks, they've been doing this a long time, and I'm curious how they have received your kind of new and innovative approach to this. And are they looking at like one for one as this a replacement for standard composites, or do they see challenges, with adopting this versus like their traditional composite material, or are they looking at it one for one?
So how they're receiving it in general, I think a lot of the traditional aerospace people are intrigued, but I think that generally they're a little bit more skeptical. For example, like the questions that we get are, this frontal polymerization has all sorts of unique voids and thermal stresses associated with this. I mean, this is like true of any manufacturing process, but they're solvable. But I think that for them, where no money's unlimited, but they're less constrained by the need to eke out tiny amounts of dollar efficiency. Where we have found incredible traction, is in wind blades, where it's like there are none of the technologies that are adopted in aerospace really have the scale and the capabilities needed for something like a wind blade. And so it's like it would be such a step change where we have found more traction on that side, and we're trying to find the industries kind of in between where the demographic of the industries and the parts we're trying to make might more fit that. In the early stages as well, even for these customers, it is a one-to-one replacement, like exploring that, because it's still a ladder to like what do the properties look like and how do we design around this. But the goal, it's kind of been in multiple phases, but phase 2 and beyond are going beyond the replacement, and now how do we use this in the broader design to get the overall cost lower. But the priority is definitely give them a part that they want, that they've already designed, and it meets their spec. Yeah.
Okay. Yeah, I think that was maybe my second question as a lead into that is what industries or what areas maybe composites hadn't been considered before do you see this being disruptive, right? Where maybe composites wasn't even looked at and now it can be considered. Like where do you see the biggest kind of opportunity?
Yeah, I guess it really depends on the bar for what you consider or looked at. Our perspective on composites, I think, is we run the opposite direction that I think. So I think because composites are difficult to make, they're quite expensive. So they've become highly engineered materials. Our perspective is if we can make manufacturing of it very convenient and extremely fast, we're looking at, when we first started, we really wanted to be in construction. And so the reason that I ask about the bar is that they're using, composite FRP rebar now, but it's like a drop-in replacement. So for us is that if the machine can produce fast enough, so if we can produce on the order of 10 to 15,000 to 20,000 kilograms an hour out of a machine reliably, now it makes sense to move the machine around. So like I would say like a lot of 3D printing companies have tried to sell that, but it's just too slow. You can't compete with a laydown area and kind of like buffer supply of materials. But then if you move the machine around, can we build like a piece of infrastructure very differently? A half a mile to a mile span directly out of the machine might change the way that we do construction. So we started So that's when we started looking at wind. Like wind was the closest thing that was already a composite that is humongous. And then as we developed the reliability of the process, we started looking at that. And then then we start to look, as we're exploring wind, we start to look at boat building. There's a lot we don't quite understand about shipbuilding and why they have steel hulls, and these are things that we're exploring. But a lot of the blade manufacturing technologies were adapted originally from boat building, and now it's like kind of going, back and forth. And so we're trying to find where like kind of construction, maritime, and wind, kind of things that look like this, where we can provide value not just in. Yeah, I don't think the value we provide really. I mean, if it's high quality, the value is weight savings. But in infrastructure and in maritime, the weight is less important. It's like if we made a worse composite that was heavier than steel, but it was way cheaper to assemble it and faster to get, like we still think we would be used. And that's what we're trying to test and understand.
Yeah. Okay. Thanks, Dan. Super interesting. Really appreciate you answering my questions. Thank you.
Yeah, thanks, Ben. Good questions, man. I see Bill Walsh has his hand up. Go ahead, Bill.
Yeah, thanks, Dan. It's very interesting technology. I had a question around like post-processing, like how much of the supply chain are you guys kind of envisioning? Do you do any, whether it be surface finish or, geometry like GD&T, like what around post protrusion machining?
Yes. Also really depends on what you want. So what we have found is that we can get a Class A finish right out of the machine, but there are compromises in how much compression we can apply. So the fiber volume fraction. But in general, if it's high volume, 5 fiber volume fractions, we get this very similar kind of surface details we might get from. It's molded up against the surface, so
Okay.
we can get a peel apply finish. We can get a kind of like standard bagging finish, and currently like. We do it by hand because we're only producing just like a few prototype parts right now. And where we want to be, I think, is still very up in the air. But ultimately, we want to develop processes that eliminate as much finishing as we can, and then from there, try to figure out if it makes sense to do more of it in-house or somewhere else. Yeah.
Well, how would you compare the surface finish of your final product to like a automated fiber placement type process?
Yeah. If we wanted to achieve, let's say they're doing AFP, they're bagging it, they're autoclaving it. Like if we wanted to achieve that quality and that compression, we are worse. The closer we get to 60 volume fiber fraction, we currently get worse. If we're in the 30 to 40%, we can get glossy finishes out of the machine. Basically, a resin rich surface right on the top. But that's also something that we are developing something. So as I mentioned, one of the things is we use a flexible die, and the more flexible the die material is, the more actuators we have to put on there. But then we're also exploring like multiple dimensions dies, and we talk about that later. But as we do that, now we're getting different surface finishes out of it. So we can impart directly that surfacing material finish onto there. And we just use kind of a very cheap material. And so we're exploring, as we upgrade that molding surface material, can we impart that directly onto the part?
Okay, well, thanks for kind of understanding surface finish. I'm also kind of intrigued with the tolerances. You said that there's, effort being put in to improve your ability to hold tolerances. Can you explain some of the constraints around that with your current process and kind of how you're planning to, improve upon that?
Yeah. One of them is the way that the part moves relative to the machine. So as we compress and we pull, these actuators are not infinitely stiff, and so they move out of plane. And so one of the ways that we are exploring that, so that's one of the largest ones. And the other one is obviously we use a flexible die, and so between where the actuators are touching, we lose a little bit of compression. And so there's a trade-off between stiffer materials allow more uniform compression, and then a softer one we just have to compensate by increasing actuator density. But So that plus like the bending out of plane. So we're exploring different ways that we move the part relative to the machine, and it's almost like a totally different machine. But that allows us much tighter tolerances. But our rates, it's far more actuators. Our rates are a little bit lower. And these are things that we're all exploring in lifetime. Yeah.
Okay. Confidence level there to be able to hit those.
Solvable,
Yeah.
100%. Will it be as cheap as we envision it is today? We hope so. Yeah. Yeah.
Okay. All right. Thanks again for your answers.
Yeah, thanks, Bill. Before we jump over to Antonio, Vincent had a clarifying question, Dan, in the chat. I don't know if you're able to see it, but essentially, could you just kind of recapture how the resin is applied when it's hardened, et cetera, and how that all works as the part comes through the machine?
Yes. So currently we don't use woven fibers. We use stitched mats. So one mat is like, let's say 1 millimeter in thickness or so, and we stack a whole bunch of them together. We would love to move to woven, and we're talking about upstream weaving and braiding technology or whatever. But what we currently do is we wet the fibers upstream. So by the time it gets to that shape changing dye, it is basically a preform. It's not like a pre-preg, like the resin is still runny. And so if you kind of look at a pultrusion process where it's like you get constant resin squeeze out, we're kind of in that stage right upstream of the dye. And then now we're adding kind of like multiple staged gates of actuators. So basically we're kind of shaping it as it goes. And then there is kind of that zone where we have that frontal polymerization line where it goes from liquid to solid, and we control where that line is. And we basically try to shape it before that front solidifies it.
Okay.
Yeah. So
Vincent,
we're going through.
Yeah, Vincent, did that answer your question?
Okay,
With
maybe
with that, let's jump over to Antonio. I see you have your hand up.
Yes, hi. Thank
Hi.
you so much for your presentation, Dan. I had a question regarding the process capabilities for your machine.
Yep.
Are you guys able to do any compound curvatures at the moment, or anything beyond, say, like 90 degrees or a certain angle of curvature at the moment with your current process? And do you have any sort of plans to sort of expand on that to do like compound curvatures if you don't already?
Yes, that's a great question, because yeah, anything that's curved is never curved in just one direction. So
Right.
we define the cross section of the shape as the XY, and then like the direction we pull as Z. We don't have a lot of limits in the XY. We have limits in like the rate at which the XY cross section changes, but not the total amount of change that is possible. Well, that's not true. We are limited by the stroke length of the actuators. So right now it's 16 inches. So we get the total cross-sectional change top to bottom is 32 inches. But that's also because that's the actuators we use, and we can also change those out. And as a startup, we use the cheapest actuators we can find, and we like kind of modify them in-house. For the Z, what we call Z curvature, we are developing that now, and that is related to Bill's question about kind of the trade-offs that we make in geometry. So the way that we currently pull straight, and so mathematically the way that we have to think about it is we have to be able to draw a straight line through the part, and then that is how we pull the part. As we're developing kind of like different concepts of pulling and kind of the shape of the surfacing material, that allows more degrees of freedom. So we're developing an airfoil component that has the tip deflection, and we're developing the way to do that. We're also kind of, that total deflection would be limited by the same height as the XY, because it's limited by the stroke length of the actuators. And we're developing that now. I would say that in about I'll send you some pictures in about 4 to 6 months.
Cool, exciting. Thank you very much.
All right, thank you for that question, Antonio. Any other questions out there? Dan, I have one. If nobody has one here, I'll go ahead and ask. My impression, and I think we've talked about this, and just for the group's perspective, is that as you talked about when you grew up, that you want to be a part producer as opposed to somebody that would manufacture like the technology and the approach that you're describing. So you would rather supply people parts using your technology as opposed to just the technology, if you will, from a manufacturing standpoint.
No, we're open to it all. I think it's
Okay.
We're so early, but one of the things that we're thinking about is even if we wanted to just provide parts, we want to provide parts that are gigantic, and so shipping itself becomes a challenge. And so I think there's depending on what it is, there may be some sort of partnerships where we move the machine to your facility, or maybe it is kind of like a providing technology and services. We don't quite know, but open to it all. Yeah.
No, very, very good. And part of the reason I ask too is just we do a lot with workforce development, education, and workforce development. And a lot of times with new technologies like this, that has to be a consideration too. Like, for example, if you were providing this as a technology to other manufacturers to use, what kind of materials, how would you train them, et cetera, things like that. But that's a little bit later in the game, but just something to kind of think through as we go work here.
Yes. Yeah. Composites definitely a lot of training needed.
Cool.
With Perseus Materials. Yeah.
Cool. So any other questions for Dan? A really, really good presentation today, Dan.
All right. Well, yeah, my email is dan@perseusmaterials.com. I'm happy to connect, and yeah, thank you all so much.
Yeah, thanks everyone. And as Dan mentioned, he provided his email. I'm happy to also provide I have Dan's contact information. If you need to reach out, please feel free to, give me a shout, and I can pass his information on to you as well. So appreciate everybody jumping in today and the presentation, and look forward to hearing more from Perseus Materials.
All right. Thank you all. Bye.
Yep. Thank you.
Thanks, Dan. Thank you, Adam.
Thanks, Dan. Thanks. Bye.